So, warm welcome to the 8th lecture on the subject of digital signal processing and its applications. Let us spend a couple of minutes in recalling what we did in the previous lecture, and let us also take a couple of questions before we proceed to discuss further on the same theme. In the previous lecture, we had looked at the operation of convolution in its own right. So, let us just quickly review the previous lecture. We had looked at convolution as an operation in its own right. And we had seen that convolution is associative and convolution is commutative. Now, a specific implication of these two properties is that because of the associativity of convolution, when I have two systems connected in cascade, they can be replaced by a single system with an impulse response given by the convolution of the impulse responses of the two systems in cascade. That was a consequence of associativity. The consequence of commutativity was that you could interchange the order of the two systems, LSI systems of course, without affecting the input-output relationship. That's right. So, these were of course specific implications of those properties of associativity and commutativity on linear shift invariant systems. But we could look at these properties as properties of the operation convolution in its own right. You do not have to always interpret convolution in the context of linear shift invariant systems. In fact, convolution is a very important operation in the context of multiplication of two numbers. I leave it to you as a challenge to come out with a connection between convolution and multiplication of two numbers represented in any radix, for example the decimal radix or the binary radix. That means numbers represented in binary or numbers represented in decimal or numbers represented in hexadecimal, base 16 or numbers represented in octal. So the challenge is come out with a relationship between convolution and multiplication of two numbers with respect to any radix, any base. Anyway, so much so, we saw that because of the associativity and commutativity of convolution, when I have a connection, a cascade interconnection of several linear shift invariant systems, you may reorder those systems in any way without affecting the input-output relationship. In fact, I left it to you as an exercise to use commutativity and associativity together to prove this, that you could rearrange a cascade interconnection of LSI systems in any way without affecting the input-output relationship. But you see, you must remember this is true only for linear shift invariant systems. If even one of those systems in the cascade connection is either not linear or not shift invariant, this cannot be said with certainty. In fact, I also leave it to you as an exercise to construct examples of systems which are not linear and shift invariant. That means they disobey one of the three properties. What are the three properties? Additivity, homogeneity and shift invariance, where they disobey one of the three properties and where when you connect them in cascade an interchange is not permissible. I leave it to you as an exercise to construct a few such examples where such an interchange is not permissible. Is that correct? Now, we also looked at the consequence of convolution or the convolution relationship between the input and the impulse response in the context of the excitation of a linear shift invariant system with sinusoids, or more appropriately with complex exponentials, with rotating phasors. So we concluded yesterday that if I excited a linear shift invariant system, so this was a part of the review again yesterday, if we excited a linear shift invariant system of impulse response Hn with a phasor e raised to the power j omega n, what emerges is h omega e raised to the power j omega n, provided h omega converges, and h omega is given by summation on all n integer hn e raised to the power minus j omega n. Of course, you can always make the index of summation k here if you like. So I can do that. Let's make it k. Provided this converges. And that was the $1 million question. When would it converge? We were looking at that. We said that a sufficient condition for this to converge is that the impulse response be absolutely summable. Is that mod Hn, when summed over all n, is finite. So the impulse response is absolutely summable. We were trying to give this a further interpretation. We said this impulse response being absolutely summable has a greater implication on input-output behavior. We showed that it ensures that if you give the system a bounded input, by a bounded input we mean an input each of whose samples can be upper bounded by a finite positive number, a finite non-negative number. Right? So we said, if this condition, if mod Hn summed over all integer n, now I am going to introduce a notation. Script z shall henceforth refer to the set of integers. And therefore, when we write summation over all n belonging to z, we mean summation of n going from minus to plus infinity, or summation over all the set of integers mod Hn. So if the summation of n over script z mod Hn is less than infinity, then we said a bounded input results in a bounded output. A bounded input leads to a bounded output. And we had defined a bounded input. Right? We had said a bounded input is one, each of whose samples can be upper bounded by a non-negative number. We call that non-negative number mx for the input x. Yes, there's a question. Just a minute. We'll take questions in a minute. So we said that an input xn is bounded if, now I introduce another notation. We'll use this notation to write there exists. So there exists an mx which is greater than or equal to 0 such that mod xn is less than or equal to mx for all n integer, of course. And of course, mx is independent of n, that's obvious. So it should be noted that we are talking about the boundedness of the samples here. We are not asking that the input be absolutely summable, no. We are just saying the input needs to be bounded. Right? But what we said is that given that the input is bounded, the output is also bounded. In that case, if mod Hn summed over all n, summed over all integer n is equal to, let us call it mh, and of course mh is less than plus infinity. Of course mh must be non-negative. If the summation is mh, then the output is bounded. Not only is the output bounded, we know a bound on the output. The output is bounded by mx times mh. That is very interesting. So we said we have a constructive conclusion here, not just an existential conclusion. The constructive conclusion is that if I know the bound on the input and I know the absolute sum of the impulse response, the bound on the output is equal to the bound on the input multiplied by the absolute sum of the impulse response. What we were asking yesterday is whether this condition is necessary for this to happen, and that is what we will now need to answer, but with a little bit of hard work. Before we embark upon that question, I would like to allow a couple of questions. Yes, there is a question from here.
Why is the limitation on mx to be?
So the question is, why should mx be non-negative? But you see, mx is a bound on mod xn. Mod xn can never be negative. So the least value of mod xn is 0. Of course, mod xn must be non-negative. So we are saying it must be the catch is not non-negative is trivial. The catch is that it is finite. Is that right? Any other questions before we work towards the necessary part? Any other questions so far? Because so far we have drawn some important conclusions. Yes, none at all? No questions at all? So then we now embark on the very important question of whether this condition is necessary. So let us pose the question first. The question is, is it necessary for the impulse response to be absolutely summable? If every bounded input produces a bounded output. Is that right? So you see, now we are asking the converse. We are saying, let the system produce a bounded output for every bounded input. So if every bounded input results in a bounded output, in other words, the system is what is called bounded input, bounded output stable. Now before we start answering this question, we would like to understand some of the terms that we are using. We call a system BIBO or BIBO stable if every bounded input results in a bounded output. Now, remember, we are saying every bounded input results in a bounded output. In a stable system, every bounded input results in a bounded output. So, it is not adequate to consider a specific example of a bounded input and look at the output and see that it is bounded and conclude the system is stable. Now, I always like to explain the idea of stability of systems by drawing a parallel to sanity of human behavior. So you may take a parallel between stable systems and sane humans, right? When would you say a human behaves sanely? When in every instance where he has a sane behavior from another human being, he responds sanely, right? So, if you behave sanely, if you behave properly with a sane human being, he or she responds with sane behavior. That's what a stable system does. Give it a bounded input, it responds with a bounded output. But you see, now take the case of a sane human being. Suppose an insane person comes in front of a sane human being. It's not necessary the sane human being would behave sanely. He may or may have, you see, it all depends on how insane that person is. If the person is all out to attack him, that person might also behave equally insanely. So even if a system is stable and you give it an unbounded input, it's not necessary the output needs to be bounded. If you give it an unbounded input, a BIBO stable system, when given an unbounded input, could produce either a bounded output or an unbounded output. Right? So what are stable systems? Those that produce bounded outputs when they are given bounded inputs, like sane human beings. Now what about unstable systems? They are also like insane human beings. Insane human beings at times can behave very sanely, even if you behave insanely with them. So you see, insane human beings are unpredictable. Is that right? Give them a bound. So similarly, unstable systems are unpredictable. If you have an unstable system, give it a bounded input, you know nothing. It may produce a bounded output, it may not produce a bounded output. Give it an unbounded input, it may produce a bounded output, it may not produce a bounded output. So it should be clear that one should not conclude that if a system is stable, then giving it an unbounded input will necessarily produce an unbounded output, or giving it an unbounded input will necessarily produce a bounded output. All that we can say is the output is unpredictable. That is for stable systems. For unstable systems, nothing can be said at all. All that can be said, in fact, all that can be said for insane people is that there is at least one instance when somebody behaved sanely with that person and he responded insanely. That's why you call him insane. If in every instance of behavior, a sane response elicited a sane input or a sane behavior elicited a sane response, you wouldn't call a person insane. You call a person insane because sane behavior elicited insane responses. And the same is true of unstable systems. I am specifying this because sometimes these finer if but, if then are not properly obeyed. Now, coming back then to the question of stability and instability, we've shown that a stable system, it is sufficient for the impulse response to be absolutely summable in order that an LSI system be BIBO stable. But we have now to ask, if a system is BIBO stable, can we immediately conclude the impulse response is absolutely summable? And again, to answer this question, we are again going to take the help of a famous story which occurs in many legends in many countries in various forms. And the story goes that there was this gentleman who knew many, many languages, and only one of them, of course, was his mother tongue. Now, the king posed the challenge before a very witty and intelligent minister to find out. In fact, that man had posed a challenge. Anybody who can find out my mother tongue will, of course, have me as his servant for a certain period of time. And of course, this person was, other than a polyglot, very knowledgeable in many ways. So the king did want to have him in his council of ministers, if possible, at least for a while. But for that, of course, the condition was his mother tongue needed to be deciphered. So what this other wily minister did was to let that person rest very peacefully on a particular pleasant night, right? And then in the middle of the night, this wily minister sent a couple of soldiers and threw absolutely cold and unpleasant water on this gentleman, rudely awakening him. And of course, you can quite guess the language in which he uttered the vindictive, the vendetta and the unpleasant things that he wanted to. His mother tongue was very quickly known, right? This teaches a very interesting lesson. If one really wants to drive a system to the brink, and a human system is no exception, use a situation which is extremely troublesome, and we'll do the same for a stable system. If we wish to prove the impulse response must be absolutely summable, drive that stable, try and drive that stable system almost to the brink of instability, like you drive a sane human being almost to the brink of insanity, to reveal or to test the person's sanity. Now here, you drive the stable system almost to the brink of instability by forcing upon it an input which is bounded in principle, but which forces the absolute sum of the impulse response to emerge. That's about the worst that can come out. Is that right? So let us then see which input to a stable system would force the impulse response to emerge. So the proof of necessity, proof that it is, hinges on the principle of a troublesome input. And that troublesome input is the following. We know that for an LSI system with impulse response Hn and input Xn, the output Yn is summation over all k Hk Xn minus k or Xk Hn minus k as we please, and consider in particular n equal to 0. Now we are going to give a particular troublesome input Xn, and we want the output, of course, if Xn is bounded, troublesome but bounded. You see, even in that story, remember, the legend goes that after this gentleman was rudely awakened from his sleep, he asked who had thrown the water. And of course, the minister very politely told him that it was raining and there was a little gap in the roof. Now what I am trying to say is that, here we are going to drive the system to the brink of instability, but we are going to do it with a sane input, a stable, a bounded input. So we will keep to the principles of boundedness, but we will still twist and turn our input to bring out the worst. And you see, assume that you are able to give this troublesome bounded input to the system. If the system is stable, the output needs to be bounded. And if the output is bounded, every sample is finite in magnitude. And therefore, in particular, when you put n equal to 0, y of 0 must also be finite, right? So we shall choose strategically choose a bounded input Xn. The output must then be bounded. If the system is stable. And if the output is bounded, then of course mod y of 0 must be finite in particular. And what is mod y of 0? Mod y of 0 is summation k going from minus to plus infinity hk x of minus k modulus of this. And now let us very wickedly choose x of minus k. Choose x of minus k in the following way. x of minus k is equal to the complex conjugate of hk divided by the modulus of hk. If hk is not equal to 0 and it's equal to 0 if hk is equal to 0. So wherever, so what you're saying is, look at the impulse response. At every point of the impulse response, if the impulse response sample there is non-zero, take its complex conjugate. Now we are allowing for a complex impulse response in general. So take its complex conjugate and divide by its magnitude. And put that in the location minus k of the input. And if that impulse response sample happens to be 0, then simply put a 0 in the same negative location on the input. Now if you do this, how much is the output y0? Clearly, y of 0 is obviously summation all k such that hk is not 0. hk, now x of minus k is hk bar divided by mod hk, and this is simply summation all hk not equal to 0 of mod hk. So of course you don't even have to worry about its non-negativity. And of course it's trivial that this is the same, obviously, I mean, this condition that mod hk or hk